Hello everyone. I'm going to talk about something a little bit strange today. Strange in more ways than one, but I think it's appropriate to do so now. I think it's appropriate to talk about this because lots of things are going on that are broadly in the realm of Olympiad results. Right? So SMO results are out, the top 30 list is circulating around, the gold, silver, bronze and honorable mentions are also kind of being released by your schools. Congratulations if you have done well, but we're going to talk a little bit about what does well actually mean. And if you have not heard the results, this is not the purpose of this video, okay? The purpose of this video is not, please tell me you have not received your SMO results and I'll chase the Singapore Math Society. That's not the purpose. Congratulations also to our Singapore IMO team. Right? Our Singapore IMO team, while I was away on reservice, which was during the exact period of the IMO and the week after, came away with 1 gold and 5 silvers, which is a great result, and much congratulations to all the students. The Olympics are going on right now as this video is being released. We have some Singapore athletes who are representing in various sports. We also, of course, have many other famous athletes from all around the world who are taking part in some sports that we may be interested in, even though there is no Singaporean representation. And this is why it makes no sense why I am coming and writing a set of definitions on partial and total orders. There's two purposes for this intro. The first is that it's a useful math concept. I want you to understand this, and it's something that all of you can grasp, and it's also a taste of what kind of things we talk about in higher level math. This is something that I learned only in 2nd or 3rd year undergraduate math. The second is that I think it has some useful implications to how we should view all these competitions. And so, philosophically speaking, it is important to have this notion, basically, of the difference between a total order and a partial order. Now, a partial order is essentially an ordering that behaves like an ordering. It satisfies these few criteria, which are called reflexivity, antisymmetry, and transitivity. Reflexive means that when I have this ordering, which I will represent using this less than or equal sign, then an element cannot be said to be bigger than itself or smaller than itself. It is equal, and so you can have this less than or equal to. The second is anti-symmetry. If A is less than or equals to B and B is less than or equals to A, then A and B are the same thing. Right? You cannot have something where A is less than B and B is also less than A. The third is transitivity. If A is less than or equals to B, B is less than or equals to C, that means A is less than or equals to C. This is what is known as a partial order, and if we are thinking of this as the usual less than or equal sign, this is extremely blatant, obvious, and you want to pause the video or close the video. Don't disappear yet, please, because what has happened is that I can add the definition of a total order versus a partial order. A total order is a partial order with the additional criteria that any two things can be compared. Any two elements are comparable makes a set and this comparison a total order. For the partial order, it is okay for A and B to be not comparable, meaning that both of these are not true. That's okay for a partial order. Now, this less than or equal sign is just what I'm using for the initial definition, but understand that the set can be anything, and this comparison, or what we will call a comparator, this comparator can be many different things. So on real numbers, rational numbers, integers, you can use the usual less than or equals to and get a total order. But we can also do other things. So on the set of English words, right? CS students will say strings. I'll just say English words. On the set of English words, alphabetical order is a total order. So if let's say that two dictionaries have the same collection of words, they should be sorted in the same order. Right? This is unambiguous, and obviously all these criteria are fulfilled. Now, an interesting one would be this divides relation. So this divides relation here means that I can say 3 divides 6. Right? Means 3 is a factor of 6. But 6 does not divide 3. So all the 3 criteria of reflexivity, anti-symmetry, and transitivity are all satisfied. So this actually is going to be a partial order, but not a total order. So from the perspective of division, for example, I can have 2 and 3, which 2 does not divide 3, 3 does not divide 2. So these two cannot be compared by division. So by division here, I could say that 3 divides 10. Sorry, no, 3 divides 12. 12 does not divide 3. 3 and 10, however, cannot be compared by division. So this is a partial order on positive integers. Now we can even come up with a partial order on major exams in Singapore. Right, major exams in Singapore. For example, this is of course not by legislation, this is just by common sense. The PSLE is going to come before, let's say, your O levels or your N levels, which would then go to your A levels. It is not possible to take the, well, I mean, it is possible, but let's just not talk about legislation. It is generally not possible for the A levels. I say must be taken before, right? So it is definitely not true that the A level must be taken before the PSLE. Now in, let's say, university, this is something that we need to make sure is true. We need to make sure that there cannot be a bunch of courses where you must take course A before course B and also must take course B before course A. Otherwise, then you're in trouble. Now in algebra, we have this comparator called majorization. Now this comparator called majorization is used in a very famous inequality known as Merhead's inequality. This video is not meant to talk about Merhead's inequality, but you can Google it if you are curious, and it is very useful for many SMO round 2 problems. Now, majorization is defined as follows. If you have got 2 sequences of the same size and non-increasing, then the first one majorizes the second one if all the partial sums of the first one are bigger than the partial sums of the second one. So x1 is bigger than y1, x1 plus x2 is bigger than y1 plus y2, the first 3 is bigger than the first 3, the first 4 is bigger than the first 4, but the last one is equal. That's the definition of majorization. For example, that means that I could say 733 is actually going to majorize the sequence 6, 3, no, I can't use 6, 3, 6, 4, 3. Right, because 7 is more than 6, 7 plus 3 is more than or equals to 6 plus 4, and at the end both sums are equal. Now it's not hard to confirm that this is a partial order based on all those definitions on top. However, there are things that cannot be compared. So for example, 733 versus 652. Now 7 is more than 6, but 7 plus 3 is less than or equal to 6 plus 5, and so therefore you cannot actually compare using this majorization operator. It's neither that the first majorizes the second, nor the second majorizes the first, so it is only a partial order. Now you might say this is very complicated, and if you have not learned Merhead's inequality before, fair enough. So if you have not learned Merhead's inequality before, you might want to think of a majorization as being silly, and instead just compare them by saying, oh, this is bigger than this if the first one is bigger than the first one, the second one is bigger than the second one, and so on. That is also a partial order. It is also a partial order because that means that in this case 733 and 643 are now not comparable anymore, because 7 is more than 6 but 3 is less than 4. So this one would not even be comparable if you use this one, this comparator. Okay. How much time have I spent talking about comparators? A bit too much. You are probably wondering what's the point of this. The video does not say comparators, it says Olympiad results. Why are we talking about this? Well, to be fair, at the top right now you see order theory. These are simple examples of what would be considered as order theory. But I want you to now view this and view lots of things under the lens of partial orders and total orders. Now that's what we do in life in Singapore in a lot of ways for everything. I'm just going to limit to math Olympiads, but sort of philosophically speaking, you can think about what this says about PSLE results. You can think about what this says about your O-level results, your A-level results, your anything really, your chess tournaments, your piano exams. I want to say a few things. The first thing I want to say is that understand Olympiad performance especially for Olympiads, as being a partial order, not a total order. If one of your friends got 20 for round 1 out of 25 and 50 upon 50 for round 2, another of your friends got 25 out of 25 for round 1 and 40 out of 50 for round 2. Now, which one would you consider to be more impressive? The one that got full marks on round 1 or the one that got full marks for round 2? Considering that both of them did quite well also on the other one. Now, we know what the SMO will rank because the first friend got 70, your second friend got 65. So we know that your friend who got 70 will place higher. But which one do you consider more impressive? Do you think it's impressive because this basically only didn't solve one question in round 2. He solved everything in round 1 and 4 out of 5 questions in round 2. He didn't solve 5 questions or make some careless mistakes on round 1, but on round 2, which is harder, he solved everything, including the hardest question of all. He solved it too. Is that more impressive? Now, in terms of level of impressiveness, which is of course not very well defined, I think we can agree that it's hard to compare. Likewise with IMO scores. Will you consider someone who got, let's say, 2 questions solved fully, IMO questions are scored out of 7, and managed to partially solve all the other questions to be more impressive? Or you consider someone that managed to fully solve 4 questions, 2 per day, but did not manage to solve and make much progress on question 3 and 6? I think I was more like the first student. When I was a student, I tended to get a lot of partial marks. Is that better? Or is it better to have some of my friends who did not touch the hard questions but could reliably solve all the questions of medium difficulty? Is that more impressive? I don't know, it really depends. Now the Olympics is going on right now. Now we know that in the Olympics, let's say that you are playing basketball. You can't win more than 1 gold medal in basketball, even if you are the best player. If you are a swimmer, you could win more than 1 medal. Now let's say the swimmer wins 2 silver medals. Is the 2 silver medals for swimming more impressive or 1 gold medal for basketball? How about 2 silver and 1 bronze? Or 1 silver and 2 bronze? Now understand that we cannot compare. Understand that we cannot compare who is better. So it always annoys me that you can't really compare some of these, but competitions are competitions, and so therefore they need to define a total order. Now imagine that if you're watching the Olympics and then after the judge says, sorry, this is a partial order, sorry, you two have played a game, I do not know who has won. You have played badminton, both of you are quite impressive, but I don't know who has won. The end. That wouldn't do, so they have to come out with a total order. That's where all the rules of all the games are. That's where the rules for Olympiads lie. So for example, in some Olympiads, the tie-breaking criteria would be who fully solved more questions, if let's say it's like round 2. The tiebreaker could be who scored higher for round 2 for the SMO. Now, I don't believe that's the tiebreak now. It used to be at some point. Now, it also depends on the rules, because for the SMO, what happens is that we are adding the 2 rounds together to determine who places first. In the US, they don't do that. In the US, the AMC and AIME just is used for qualification, and then the scores are wiped clean, and then whoever does well for the US AMO just gets the US AMO winner award, independent of what they got for the AMC and AIME, as long as they got it. Now think about it, right? Would you consider it to be better if somebody barely qualified for the US AMO and then just got first place by perfect score in US AMO, or someone who got perfect score in the AMC and AIME but then just did average on the US AMO? It depends. The SMO adds up the scores. Do we prefer that? Now, most of us are therefore conditioned to think in terms of competition rules, and that is good 1 month before the competition. 1 month before the competition, you must make sure you know the rules. At the Olympics, there's what's called a recce, which means that, let's say, for like a marathon or for cycling, the athletes are going to go there and look at the route first so that they familiarize with that specific route. And let's say they realize that, oh, this route actually is very hilly. It has a lot of mountains. Now that is advantageous for some of them, and then they know that they have to plan accordingly. But on another location, they may not like it as much. So competitions always have a total order, but it's okay to view things differently and to say that I'm really good at the SMO round 1, I'm not so good at round 2, I just really like round 1, I like to solve questions quickly. That doesn't get you as good at SMO result, but it's okay. The SMO adds up the scores. Now if you're in the USA, that will be even worse. You will not get any award for the US AMO if you just like to do the AMC and AIME. But you will be recognized as having got a distinction for the AMC and AIME. Are you happy with that? It depends. Now, another thing is just about the set. We're talking about post sets, partially ordered sets and totally ordered sets. Every time when we're trying to order things, what happens is that we like to say, oh, who is better? And sometimes we apply that to ourselves. How come I got worse, right? So we said, last year I got a gold, this year I only got a silver. I got worse. Then I got a bronze, that's even worse. Is that really right? Is that really fair? Let's say you got a gold this year on the SMO Senior. The next year you got a silver on the SMO Open. Does that compare? Now, if you were to just say gold and silver, of course a gold is better than a silver. But if you're talking about gold on the Senior versus silver on the Open, that will be different. But even if it's the same competition, you know the context. And so the set basically that I'm referring to is that you need to account for the entire context. Now, some of you play sports, some of you do music, some of you are in a big family and you need to take care of your siblings, and that all makes an impact. How we order it is going to be very debatable as a result. But even if we put aside all of these like sort of demographic factors and we just talk again about the competitions, there is a lot of randomness involved in a competition. I feel like as a result of this randomness, one could say that the best possible way of comparing the performance of, let's say, students is to think of it as each student is actually a random variable. You are a random variable. I am a random variable. If I were to take the IMO today, our Singapore IMO team were to take the IMO today, you were to take the IMO today, or the SMO, or anything, the competition and our ability kind of leads to some randomness. There are different probabilities, and so one possible partial order for random variables is as such. So if X and Y are two different students, or it's a student you this year and Y is you last year, if I think that my chance of getting above 80% is better than my chance of getting above 80% last year, my chance of getting above 50% is also better than my chance of getting above 50% last year, my chance of getting at least 20% is also better than my chance of getting at least 20% last year, I've improved. I think this would be considered as I've gotten better. Or if you like to compare with your friend, you can say you think you're better than your friend. But it is a random variable. It's a random variable, and each competition, each contest is a very small sample size. And if you talk about one contest, it's a sample of size 1. On behalf of my students, I kind of take offense and I get annoyed. I also get annoyed whenever teachers talk to parents, parents talk to students, students talk to teachers, and sort of use one result in order to try to extrapolate way too much more than they should. Even if you did better last year than this year, it does not mean you have gotten worse. And I say this in terms of score or ranking, right? If your ranking goes down, that doesn't mean you've gotten worse. Maybe someone else happened to do better. There's randomness involved. Maybe it's just the questions were harder, so your score went down. And of course, there are a whole lot of factors in the SMO or in IMO. For those of you who are familiar with the IMO, you will know that one example was this year's IMO Q5. This year being 2024, if anyone's watching this much later, this year being 2024, IMO Q5 was a very high variance question. Now, I don't want to spoil it. If you haven't tried it, please try it. It's a fun question. If you're not doing it in a competition context, it's really fun. But what happened is that it's a high variance such that very, very, very good students found it to be hard, and some students who maybe were less good or less experienced or less knowledgeable actually found it easy. There are questions like this. As a result, results change. Now, as another example, I would just, without trying to give away too much due to respect for the participants, I would say that the relative ranking of, let's say, our Singapore team on this and other years' IMOs are not the same as their ranking on the national team selection test. Very often, a student that does really well for the national team selection test may happen to not do so well on the IMO and vice versa. It's unfortunate that people do not know how well the students did on the national team selection test, but they do know how well the students did on the IMO, and so that becomes their picture. Again, I feel that's a little bit of an injustice, and so we should be a bit careful to judge. But also, if you are the person involved, just recognize that you know yourself. You know yourself whether you got what you deserved, and you know yourself if, let's say, the questions favored you or were not in your favor, and you know what it tells you, even if no one else understands. It's the same thing even as we are watching the Olympics, especially for a sport that we don't know, we only have a sample size of 1. If any of you are watching a new sport, you would assume that the person who won the gold medal is the best. That is probably not true, just simply because the chance of the best person winning is usually less than 50%. Now, I've said a lot about this, and so I need to kind of track back a little bit and say that this is a partial order. I want to say that competition results are a partial ordering, or at least we can impose many different partial orders on it as to what do we consider as better. The definition of better can be different, but it's not nothing. It's not an empty order. And so there's been this counter movement as well of people saying that don't bother about competition results. These are just for kiasu people. These are just for people who have way too much time on their hands, and then they cram and mark. This is very wrong too. So I don't want that impression to be what you take away from this discussion. Any awards that you can get are mightily impressive, and any awards that your friends have gotten are impressive. So I want to say again, much congratulations to our Singapore team at IMO, and much congratulations to all of you on whatever awards you have gotten on the SMO. if you've gotten something better than you expected or something worse than you expected, you know yourself. But it is still, in the random variable sense, it's still a data point that gives you some information about where you're at. And so when someone does very well, you or someone else, it is information. So don't take this the wrong way and say that this all doesn't matter. I just go and do it for fun. You should put in proper effort, and you should also use each competition, let's say the SMO round 2 if you took it recently, or even the SMO round 1, and to identify your areas of strength and weakness. It is information. It's just that if let's say that someone is better than you at algebra and combinatorics and geometry and number theory, they are better than you. It is a partial order. But if you are better than them at algebra and combinatorics and they are better than you at geometry and number theory, you can't be compared. And the results will differ each time. Now, this started off as a math video, so I want to end this off as a math video. Here is an IMO shortlist question from 2023. The IMO shortlist is something that is released after the next year's IMO, so this is relatively hot off the press. This is a combinatorics question coded C5, so it's the fifth in the fifth easiest question in the shortlist out of 8, somewhere in the middle. I'll include a link to the problem below, but if you want to screenshot this, give it a try. The hint that I want to give to this question is that this is also related to what we have been talking about in this video. I'm not going to say in what sense, but it is actually useful to have this notion of different types of orderings in solving this problem. It is very often the case that understanding math well also helps us to understand the world a bit well. So what I'm presenting this video is actually kind of taken from an essay that I wrote in my university studies, although of course in a slightly different context. And I hope that for all of you that do math also recognize that math gives you an understanding of things around you, right? Things like statistics, understanding randomness. You do probability questions, you know that there is always going to be a chance that someone who on average does worse happens to do better sometime. And you know that sometimes it's not possible to compare based on what we've just talked about from partial orders and total orders. So for this question here, how do we actually try to show that Elisa can make things good depends on a measure of goodness, and the measure of goodness is based on a comparator, and that's as far as I'm going to say for this. Let me know in the description below if you've figured out what sort of strategy and comparator there is for this problem. As always, feel free to chat about competitions as well, about your SMO results and about any other competitions. I think it's fun to talk about as long as we have the right understanding of it. Thanks for watching this relatively long monologue, and see you soon. We'll be getting back to solving some actual full-fledged math problems soon.